In high-dimensional statistics, the sample covariance matrix is a liar. When the number of features approaches the sample size, extreme eigenvalues are systematically biased, distorting risk estimates and breaking portfolio optimization. We start with a data matrix X with n rows and p columns. Each column is a feature, each row an observation. We standardize each column to have mean 0 and variance 1. The sample covariance matrix is simply X transpose X divided by n. This matrix captures how features move together. But when p is large relative to n, this matrix becomes unreliable. The sample covariance is a noisy estimate of the true covariance, and the noise grows with the dimension. This is the root of the curse of dimensionality. The reason is that with limited observations, the estimation error in each covariance entry accumulates, and the matrix as a whole becomes ill-conditioned. As a result, the eigenvalues of the sample covariance matrix deviate significantly from the true eigenvalues, leading to distorted risk assessments and unreliable portfolio optimization. The Marchenko-Pastur theorem describes the distribution of eigenvalues when both n and p go to infinity, with their ratio fixed. The eigenvalue density is given by this formula, where sigma squared is the true variance, and c is the ratio p over n. The bounds lambda plus and lambda minus define the support of the distribution. For independent data, sigma squared is 1. This theorem tells us exactly how the eigenvalues spread out, even when the true covariance is the identity matrix. It reveals that the sample eigenvalues are not concentrated around 1 but are spread over an interval determined by c. This spreading is a direct consequence of the finite sample size and the high dimensionality. The theorem provides a precise characterization of the noise-induced eigenvalue dispersion, which is essential for understanding the bias in extreme eigenvalues. The theorem gives explicit limits for the largest and smallest eigenvalues. The largest eigenvalue converges to 1 plus the square root of c, all squared. The smallest converges to 1 minus the square root of c, all squared. For c equals 0.5, the largest eigenvalue is about 2.91, while the true value is 1. The smallest is about 0.09, again far from 1. This is a massive distortion. The spectrum is stretched, with extreme eigenvalues over and underestimated. This bias arises because the sample covariance matrix, when inverted, amplifies the errors in the smallest eigenvalues, leading to unstable estimates of the inverse covariance matrix. This has direct implications for portfolio optimization, which relies on the inverse covariance matrix to compute optimal weights. The distortion in eigenvalues directly translates into distorted risk estimates and suboptimal portfolios. This chart shows the dramatic distortion. The true eigenvalues are all 1, but the sample eigenvalues range from 0.09 to 2.91. The largest is almost 3 times the true value, and the smallest is nearly 0. This distortion has profound implications for risk management. If we use these eigenvalues to estimate portfolio risk, we will overestimate the risk of high volatility assets and underestimate the risk of low volatility assets. For example, consider a portfolio with 2 assets, one with true volatility 20% and another with 10%. In high dimensions, the estimated volatility of the first might be inflated to 30%, while the second might be deflated to 5%. This leads to a misallocation of capital, as the optimizer will perceive the first asset as riskier than it is and the second as safer, resulting in a portfolio that is not truly optimal. The Markowitz mean variance optimization relies on the covariance matrix to balance risk and return. But with a distorted covariance matrix, the optimizer sees high risk for volatile assets and low risk for stable ones. This leads to extreme portfolio weights. It overweights low-risk assets and underweights high-risk ones, often resulting in concentrated positions. In practice, this is why Markowitz optimization often fails. It amplifies estimation error, turning noise into extreme bets. The reason is that the optimizer treats the estimated covariance matrix as if it were the true one, and since the estimated matrix has extreme eigenvalues, the resulting weights are extreme. For instance, a small misestimation in the covariance can lead to a portfolio that is heavily concentrated in a few assets, which is risky and not diversified. This is a well-known problem in quantitative finance, and it highlights the need for more robust estimation techniques. Another counterintuitive consequence, even when all variables are independent, you will observe many significant correlations. For n equals 250 and p equals 1000, the expected maximum sample correlation is about the square root of the natural log of p over n, which is roughly 0.168. This means that in a typical factor mining exercise, many discovered factors are just noise. The curse of dimensionality creates phantom relationships. This occurs because with many variables and limited observations, the sample correlations are not zero but have a distribution with a positive maximum. This is a statistical artifact. The maximum of many random correlations is likely to be large. For example, if you test 1000 independent variables against a target, you might find a correlation of 0.168 purely by chance, which could be misinterpreted as a real relationship. This leads to false discoveries and unreliable factor models. In practice, factor models often report hundreds of significant factors. But many are spurious. The expected maximum correlation of 0.168 means that even with no true relationship, you will find correlations that appear economically meaningful. This is why factor investing strategies often underperform out of sample. The discovered factors are not real, they are artifacts of high dimensionality. This is a fundamental challenge for quantitative finance. For instance, a factor that shows a strong correlation in sample may have no predictive power in a new dataset, leading to disappointing returns. The reason is that the in-sample correlation is inflated due to noise, and when applied to new data, the noise does not repeat. This is a classic example of overfitting, and it underscores the importance of out-of-sample validation and the use of techniques like shrinkage or random matrix theory to filter out noise. Let's compare the low-dimensional and high-dimensional regimes. In low dimensions, the sample covariance is a reliable estimate. Eigenvalues cluster around the true values. In high dimensions, the spectrum is distorted, with extreme eigenvalues far from the truth. This comparison highlights the curse of dimensionality. The same estimator behaves very differently depending on the dimension-to-sample ratio. In low dimensions, the estimation error is small because there are enough observations to estimate each covariance entry accurately. In high dimensions, the number of parameters grows quadratically with p, but the number of observations n is fixed, leading to a situation where the sample covariance matrix becomes singular or ill-conditioned. This is why the eigenvalues spread out. The matrix is trying to fit too many parameters with too little data, resulting in overfitting and noise amplification. Here are the key numbers from this analysis. For c equals 0.5, the largest eigenvalue is 2.91, the smallest is 0.09, while the true value is 1. The expected maximum correlation for n equals 250 and p equals 1000 is 0.168. These numbers illustrate the magnitude of the distortion and the prevalence of spurious correlations. The eigenvalue distortion means that if you use the sample covariance matrix to estimate risk, you could be off by a factor of nearly 3 for the largest eigenvalue, leading to a significant overestimation of portfolio risk. Similarly, the spurious correlation of 0.168 might seem small, but in the context of factor investing, it can lead to the selection of factors that have no real economic basis, resulting in poor out-of-sample performance. These numbers serve as a reminder of the dangers of high-dimensional data and the need for caution. What can we do? First, be aware of the bias. Second, use shrinkage estimators that pull extreme eigenvalues toward the average. Third, consider random matrix theory to clean the correlation matrix. Finally, always validate factors out of sample. These techniques help mitigate the curse of dimensionality. They don't eliminate it, but they make our estimates more reliable. Shrinkage, for example, works by combining the sample covariance matrix with a target matrix, such as the identity matrix, in a way that reduces the variance of the estimator at the cost of some bias. This trade-off is often beneficial in high dimensions. Random matrix theory provides methods to identify which eigenvalues are due to noise and which are due to signal, allowing us to filter out the noise. Out-of-sample validation ensures that any discovered patterns are not just artifacts of the sample. By applying these techniques, we can improve the robustness of our risk models and factor strategies. In high dimensions, the sample covariance matrix is a distorted mirror. It overstates risk for volatile assets and understates it for stable ones, breaking Markowitz optimization and creating spurious factors. The Marchenko-Pastur theorem quantifies this distortion, and the numbers are stark. But with awareness and proper techniques, we can navigate this curse. Shrinkage, random matrix cleaning, and rigorous out-of-sample testing are essential tools. As quantitative analysts, we must always question our estimates. The curse of dimensionality is not a dead end, it's a challenge to be managed. For example, by applying shrinkage to the covariance matrix, we can reduce the extreme eigenvalues and bring them closer to the true values, leading to more stable portfolios. Similarly, by using random matrix theory to identify and remove noise eigenvalues, we can improve the signal-to-noise ratio in our data. These methods are not perfect, but they are practical steps toward more reliable analysis in high-dimensional settings. Markets reward discipline, not certainty. If this analysis helped, like the video and subscribe to Deep Quant. Tell us in the comments which market idea we should test next. Evidence beats noise. Control risk before chasing returns.